Okay, hello Math Counts friends. Today I'm starting a series of 6 videos with some really cool geometry, and I've represented each of the 6 ideas here with a little different colored drawing. The one that I'm going to start with is over here in the pink, so let's jump right in. Alright, so let me redraw that figure. What we're talking about here is something that's called, I don't know if it has an official name, but I'm going to call it the cyclic quadrilateral. Cyclic quadrilateral supplementary angles theorem. Alright, that's a big mouthful. Theorem. Oop, there we go. CQSAT, cyclic quadrilateral supplementary angles theorem. We'll call it that. Alright, so, okay, that took up a lot of space. I'm actually, maybe I'm going to erase that so that we have room to do what I want to show you here. Okay, so here's what we need to know. Basically, if you have any 4 points that you pick on a circle, so you can pick any 4 random points. We might pick this one, I don't know, let's do this one, and I don't know, this one here. So you pick any 4 random points on a circle, and then you draw the lines that go through the pairs of neighbors, right? So something like that, something like, that's not exactly right. Let's see if I can do better. That's pretty good. And then like this, and finally this line here. That forms a quadrilateral, okay? All right, and the thing about this quadrilateral is all of its vertices are on the circle. And that makes it a cyclic quadrilateral. That's the CQ, cyclic quadrilateral. And the supplementary angles part is that if you take any 2 opposite angles, okay, so for example, let's take this one here and this one here, they will be supplementary. By supplementary, I mean that the 2 angles add up to 180 degrees. So these 2 are going to be supplementary. So that's the S. Cyclic quadrilateral supplementary angles. Supplementary angles theorem. And at the same time, if we take the other opposite pair, this one and this one, those will also be supplementary. And so maybe I shouldn't draw them in the same color if they're supplementary, because they're not equal to each other. But maybe what I'll do instead is I will draw, oops, put back my SA here. I will draw the angle that's supplementary to this one. There's another angle that's supplementary to it right here. And also there's another one right here. And so those angles are actually all equal. This one, and this one are all equal. And at the same time, this one is going to be equal to the angles that are supplementary to this one. So that's this one here and this one here. Okay, so those angles are also all equal to each other. And I can go further and I can say that this angle here is going to be the same as the ones that are supplementary to this, which is here and here. And I guess the green and yellow look a little too similar, but let's use gold here. Then we've got this one is equal to the angles that are supplementary over here, so this one and this one. Okay, so those angles that are all the same color, they're all equal to each other. And it doesn't matter what 4 points you pick on the circle, this will always be true. And it turns out that this is really useful. So if you want to have a proof of this, you can keep watching this video, because I'm going to go ahead and prove this. But if you're not interested in the proof, feel free to stop at this point. Okay, so let's go ahead and jump in with the proof. All right, so I'm going to draw my circle again, something like that, and I'm going to draw my 4 lines across that are going to form the 4. And maybe I'll try to make it look a little different this time. I don't remember exactly how it was before, but let's go all the way over. Oh yeah, that's going to be a kind of an extreme one here, where it's very short there. Actually, no. Let me make it a little bit. That way we won't have to worry about that tiny one. It's gonna. I need some room to draw things. Actually, let's see. Get that to go through those points. All right, great. So now we've got our quadrilateral, our cyclic quadrilateral. And the first thing I'm going to do is I'm going to draw the center point. And I'm going to draw the radiuses from the center out to each of these 4 points. And what you will notice is that by drawing these 4 radiuses, I'm splitting my cyclic quadrilateral into 4 isosceles triangles. Okay, 1, 2, 3, 4 isosceles triangles. So these were random points, and on the circle, and I've been able to split it into 4 isosceles triangles. That's always going to be true, because why is that? It's because these radiuses are all the same length, right? And so these triangles out here are all going to be isosceles, and when you have an isosceles triangle, that means that the angles here are going to equal each other. So those 2 angles are going to be the same, and these 2 angles are going to be the same, and these 2 angles are going to be the same, and these 2 angles are going to be the same. So let's give those angles names. We'll just make up some variables to describe those. So let's call this first one A. So that's angle A. That's also angle A. And then let's just call the next one B. This is B and B. Let's call the next one C. We've got C and C. And the last one we'll call D. I got 2 blues. That was probably a mistake. But anyway, we got A, B, C, and D. And the angles that we were interested in are sums of pairs of these angles. So this interior angle of this point here, this interior angle is actually A plus B, or we could also look at this vertical angle there. It's the same thing. That's A plus B. And you've got over here, you've got B plus C. That's equal to this whole angle in here. Right? So this A plus B is equal to this whole angle in here. This whole angle here, D plus C, that's equal to this one here, D plus C. And then this one in here, D plus A. We've got D plus A. And since those are all the interior angles of this quadrilateral, they have to add up to 360 degrees. So we got 360 degrees is the sum of all those angles. It's A plus B, oops, A plus B plus B plus C plus C plus D plus D plus A. And we can, of course, rewrite this as equal to 2 times the quantity A plus B plus C plus D. Okay, because we got 2 A's here, one at the beginning and one at the end. Then we've got these 2 neighboring B's, 2 neighboring C's, and 2 neighboring D's. So it's all 2A plus B plus C. So that means if I divide both sides by 2, I've got 180 is equal to A plus B plus C plus D. And now we're pretty much there, because look, if you add up these opposing angles, doesn't matter whether you pick this pair or this pair, both of them are going to be A plus B plus C plus D. So if you look here, you've got an A, a B, a C, and a D. And if you look here, you've got an A, a B, a C, and a D. So that means these two angles add up to 180, and these two angles add up to 180. So the opposite angles are supplementary. The opposite angles are, those pairs add up to 180 whenever you have a quadrilateral that is cyclic. And it turns out that the converse is also true, meaning if you just take any random quadrilateral and you measure the angles and you find that they have opposing angles that add up to 180 degrees for both pairs, you're going to be guaranteed that those 4 points are going to fall on a circle exactly. So whenever you have a cyclic quadrilateral, it'll always have its opposing angles add up to 180 degrees. And whenever you have a quadrilateral with opposing angles that both add up to 180 degrees, it will be a cyclic quadrilateral, meaning that its points all fall on a circle. I guess we didn't prove the converse, but I'm just telling you that one's true. But anyway, that's a cool little proof. And it turns out that this theorem is really useful to prove something called power of a point. Power of a point, and we're going to get to that in either the next video or the one after, so stay tuned. All right, thanks. See you in the next video. Thanks for joining.